Stoichiometry. Well, if you haven't watched my first video on Stoic, you should probably start there. But this video will talk about the guided notes for stoichiometry, which you will all be receiving a paper copy of in our classes. So, what is Stoic? What is stoichiometry? Quantitative analysis of chemical reactions. I got good news and bad news. The good news is you already know how to do this math, and you've been doing it your whole life in the context of things like cooking or interacting with quantities, really, in any case where there's a process involved. But the bad news is when we talk about it in the context of chemistry, dealing with chemical formulas, mass, moles, things like that, students have a tendency to freak out about these things, even though the conversions between these units, it's all the same math. If you know how to multiply and divide and pay attention to the units of the numbers that you're using, this really won't be that bad. And that's what these guided notes are going to try and help us figure out. So let's talk about this, shall we? Here we go. Key concepts in stoichiometry. All right, we have this thing called a mole ratio, right? If you think about converting units in chem so far, we've talked about converting from grams to moles, and we also know how to convert from moles to grams. Well, if you think about those as separate steps, there's a step in the middle here where we go from grams to moles. We need to go from moles of one thing to moles of something else to help us understand, well, if I have a certain number of grams of one reactant, how many grams of the product can I make? Well, I have to convert from grams of this thing all the way to grams of something else. How do I get there? I have to take a pit stop at moles. So I go from grams to moles of one thing to moles of something else, and then moles of that thing to grams of that thing. The nice thing about this is we can set up our calculations very clearly. It takes some time to set it up, and we have to be careful about this. But once we have it set up, all the math is the same, multiplying and dividing. So, take some time to read through this here with me. The only way stoichiometry works is if you're using a balanced chemical equation. We balance equations to follow the laws of conservation, but this is particularly important in stoichiometry. The coefficients of the balanced equation show us the ratio of moles for each substance required for the reaction for it to run, or whatever in terms of the reaction components. So we'll look at this really crummy recipe for bread. It says 4 parts flour, 2 parts water, 1 part eggs, and 1 part yeast gives us 1 loaf of bread. So let's just talk about this for example. If we had 8 cups of flour, right, 8 parts flour, and an infinite amount of stuff, we could make 2 loaves of bread, right? If we had a dozen eggs, and an infinite amount of flour, water, and yeast, well, we could make 12 loaves of bread, right? These these coefficients tell us the ratio of these ingredients. For instance, for every 2 parts water, I need 1 egg. Okay, so if I have 6 cups of water that I want to use, I would need 3 eggs to make that work. These ratios between our coefficients tell us how the equation will operate, how many parts of each thing are needed, or how many parts of each thing will be produced. And the same thing is true for a chemical equation like this here. Methane and oxygen combust to form CO2 and H2O. Well, for every 1 molecule of methane that I use, I'm going to produce 1 molecule of CO2 and 2 molecules of H2O. Obviously, that's 1 molecule of methane reacting with 2 molecules of oxygen to make 1 molecule of CO2 and 2 molecules of H2O. But in chemistry, we're never talking about 1 molecule at a time. We're talking about moles, right, or grams. But we have to use moles to equally compare the quantities of substances, which is why we must be working with moles at some point in stoichiometry. So, let's start with this. Examples 1 and 2. We're going to see how a mole ratio, relating the moles of one substance to the moles of something else, using our balanced chemical equation, can help us see how the the coefficients in our equation tell us the relationships between these quantities. So, we use mole ratios to find out how many moles of another reaction component are needed or will be produced, like these calculations below. Assume we start with 3 moles of H2 and 1.5 moles of O2. How much H2O will we make? Well, I'll start my calculation here, 3.0 moles of H2 over 1. Now, I'm going to multiply this by a mole ratio, just like I was converting units in grams to moles or moles to grams. So the unit of this denominator must have the same units as the previous. Numerator, moles of H2. And I'm trying to find out how many moles of water we will make. So can I relate the moles of hydrogen to the moles of water? Absolutely, because they are part of the same balanced chemical equation. So what this equation is telling me is that for every 2 moles of hydrogen that I use, right, 2 moles of hydrogen that I use, I will make 2 moles of water. Now this one calculation here assumes that we have enough oxygen to do this, which in this case I can assure you that we do. And we will consider scenarios like that later that are a little bit more complicated. But to finish this math, we multiply across the top and then divide by each number on the bottom. 3 times 2 is 6, divided by 2 is 3. Now, those are the numbers. Moles of H2 will cancel out because we have it in the numerator and denominator, leaving us with the units of moles H2O. What does this calculation say? Anytime you do the math like this and convert units, you need to think about what the calculation says, like a sentence. If I use 3 moles of hydrogen, I will make 3 moles of water. That's all it's saying. Now let's do the calculation for oxygen. 1.5 moles of O2 over 1. Same units from the numerator go into the next denominator, that's moles of O2. And we're trying to see if I use all of that oxygen, how much water can I make? Moles of H2O. So here we go. In this equation, it tells me for every 1 mole of oxygen, because the coefficient is not there, which means it will tell us the coefficient is 1. For every 1 mole of oxygen, I will make 2 moles of water. So 1.5 times 2 is 3, divided by 1 is still 3. Moles of oxygen cancel out, leaving us with moles of H2O. So what does this calculation say? If I use all 1.5 moles of oxygen, I should make 3 moles of water. Fair enough. Now we can go the other way as well. In this second example, I say that we've produced 5.4 moles of NH3. That's how much we made. How much did we have to use from our reactants? It's the exact same math, it's just solving for something else. We start with what we know, 5.4 moles of NH3. The denominator of the next term will have the same units, moles of NH3. This guarantees that those units cancel out. First, we're going to solve for the moles of nitrogen that we used to make this much ammonia. In the chemical equation here, it says for every 2 moles of ammonia that we produce, we must have used 1 mole of nitrogen. When I do this math, 5.4 times 1 is 5.4, divided by 2 is 2.7. Moles of ammonia cancels out because it's in the numerator and the denominator. Good. Leaving us with the units that we are looking for, moles of N2. What does this calculation say? If I completely produced 5.4 moles of ammonia, I must have used 2.7 moles of nitrogen. Okay, let's find out how much hydrogen we had to use. Starting the same way, 5.4 moles of ammonia. Units of ammonia, moles of ammonia, go in the denominator here. It's not enough to just say moles. It's not enough to just say ammonia. You have to say moles of ammonia. Okay. For every 2 moles of ammonia that I produce, I will make 3 moles of hydrogen. 5.4 times 3, I just want to verify this here, 5.4 times 3 is 46.2, divided by 2 is 23.1. Hello? 5.4 times 3. Oh, I did 15.4 times 3. Excuse me. I knew that didn't look right. 5.4 times 3 divided by 2 is 8.1. That makes sense. 8.1. Moles of ammonia is in the numerator and denominator, so those units cancel out, leaving us with the units we are looking for, moles of hydrogen. What does this calculation say? If I completely produced 5.4 moles of ammonia, I must have used 8.1 moles of hydrogen. So the math in both of these examples looks exactly the same. You start with what you know, that is these. You start with what you know. You multiply by the mole ratio that will get you what you're looking for, and then there's your answer. You just do the math. To get what you are looking for, the numerator of the last term has to have the units that you are looking for, and of course the corresponding number that matches those units. Then once you do the math, you cancel out your units appropriately and make sure you operate the numbers correctly, and you will get your answer. I want to do one more example here with number 2 that's a little bit extra. Let's prove that if I actually used 2.7 moles of nitrogen, do I really need to use 8.1 moles of hydrogen? Let's see. I'll start with 2.7 moles of nitrogen. Just to prove to you that you can do this in any direction. Start with something you know, and then use the chemical equation's mole ratio to find your answer. I'm trying to see, for every 1 mole of N2, because the coefficient here isn't written, so it's a 1, I will need to use 3 moles of H2. 2.7 times 3 is 8.1. Divided by 1 is still 8.1. Moles of nitrogen cancels out, giving me moles of H2. What does this calculation say? If I completely use 2.7 moles of nitrogen, I must also use 8.1 moles of hydrogen. And that makes sense because this right here, 2.7 and 8.1, is in a 1:3 ratio with each other. Right? For every 1 mole of nitrogen we use, we have to use 3 moles of hydrogen. And these numbers follow that pattern as well. Stay tuned for the next video where we go over the next page of these guided notes.